So the rough plan for today is as follows. First, I will talk a bit about my own research, one paper that we have recently written. This part will be around 15 minutes, and I will use that to kind of set up the stage. For the kind of workshop / hackathon that we are doing afterwards. In this hackathon, we will look at GPT 3.5 and investigate different prompting techniques and see how these prompting techniques affect the behavior of these models. And I think this will be fairly lighthearted. I don't think it's too cognitively taxing, so hopefully we can use this session to all slowly wake up for the rest of the day. The hacking workshop part will be roughly 45 minutes. It's a bit flexible. I will be available for questions during that time, but basically it's just you code up some stuff. And then at the end, we will meet again, discuss some of the results and what you found, and that concludes the session. So let's start with the first part. I think the whole day today is about large language models, if my knowledge is correct. I assume you already have at least some ideas what these models are, but to summarize it again, large language models are really big neural networks that are trained on vast amounts of data to simply predict the next word that follows a given text sequence. So they receive a text sequence and they simply try to predict what word or token will come next. Okay. Well, what is really cool about these models is that their abilities go far beyond the mere generation of text. And in fact, as these models were scaled up, both in terms of number of parameters and in terms of the training data set size that these models were trained on, many new abilities emerged. And these abilities are sometimes also called emergent abilities because the presence of them in the bigger models could have not been predicted from merely looking at the smaller models. And by now you have models such as PaLM 2 or GPT-4 that can solve a variety of tasks. They can translate from one language to another. They can solve challenging reasoning problems. They can write computer code and so on. About a year and a half ago, I think by now, we started to wonder in our lab whether we can take some of these models and actually place them into a psychology lab and let them do psychological experiments. And this idea is kind of interesting because it allows us to look into the black boxes that these models are and use the same tools that psychologists have used to understand human behavior, to understand how large language models reason, how they make decisions, and so on. In this paper that is now published at PNAS called Using Cognitive Psychology to Understand GPT-3, we looked at a large battery of canonical experiments from the literature. And then tested GPT-3, a particular large language model, on some of these experiments. One of the first things that we looked at is sometimes called a decision from description setting. So here a problem looks something like that. Imagine that we give you $2,000 right now to play a game, and then we ask you which of the two options you prefer. Option F has a 50% chance that you will lose $1,000, or option J has a 100% chance that you will lose $500. And then you simply have to say which of these two options you like more. And you can give such problems to a large language model by simply prompting it with the text here and letting it complete the text with either option F or J. We did this on a large data set of such problems, sometimes called the Choice of 13K data set. And we tested different models in the GPT-3 family, ranging from the least complex model, the ADA model, to the most complex model, the Da Vinci model, on this data set. And we also compared the performance of these models against human performance. This plot here shows these different models, the GPT-3 models in blue and humans in orange. And on the y-axis, you see the performance of these models measured in terms of regret. Regret here, this means lower regret means better performance. And what you can see is that the less complex models, the ADA model, the Babbage model, and the Curie model actually do not perform above chance level on this kind of problem setting. But the Da Vinci model actually is able to solve these decision-making problems above chance level. Question?
compute or like to understand what they're computing, and now we still don't really know what is being computed when they do this.
Exactly right. I mean, these models are not black boxes according to the strictest definition, because we have maybe access to all of the weights, all of the activations, at least in these open source models. But still, even though we have that, there's like really complex operations that these models are doing that we cannot understand by just looking at the weights or activations. So in that sense, it can be a reasonable approach to just look at their behavior and try to gain some insights into how they work by just looking at behavior. Yeah.
You said the lower mean regret affects the performance, but the example that you gave, I think the expected value was both using $500.
Very good observations. Yes, in this case, in the example from before, both of these options are equally good. So there, no matter what you choose, you have a regret of 0. But there are a lot of problems where that is not the case. So what we see is these kind of the ability to solve these decision-making problems is an emergent ability in these larger models, in particular this Da Vinci model here. And what we can also observe is that the performance of the Da Vinci model does not reach quite human performance yet. But I think if you would repeat this whole experiment with the latest generation of models, this gap would further close, or maybe the models would be even better than the people. But for me, what is more interesting is the observation that both people and the large language model are not perfect on the task, as indicated by having a regret larger than 0. And that means they make mistakes. And maybe it could be possible that they make structured mistakes, that they have certain cognitive biases. And we can now go out and test whether GPT-3 has some of the cognitive biases that researchers have identified in people. And we did that in the paper, and we found that GPT-3 showed some of these cognitive biases that are also present in people. For example, it showed a framing effect, certainty effect, and an overweighting bias. I don't go into the details what all of these mean. If you're interested more in this, feel free to check out the paper. But then at the same time, we also found that GPT-3 does not exhibit some of the biases that people are known to have. For example, for the ones that we tested, that included a reflection effect, an isolation effect, and the sensitivity to magnitude perception. So again, I won't go into the details what all of these things are. If you're interested into diving deeper into this, I recommend you checking out the paper. Then the second setting that we looked at was a decision from experience setting. And in particular here, we looked at the paradigm that is called the horizon task. The horizon task is a two-armed bandit experiment where participants have to repeatedly select between two possible options. There is a red option and a green option. And whenever you select one of these options, you get feedback in terms of how rewarding these options are. And then you have to repeatedly interact with a problem and over time accumulate as much as rewards as possible. To solve this task efficiently, you have to trade off between exploiting the knowledge that you currently have, but also exploring parts of the environment that you don't know anything about yet. And people do that using two different types of exploration strategies. There's one strategy called random exploration, which essentially involves adding noise to your decision-making process. So sometimes randomly you select the action you think is worse, because in the long run that could lead you to accumulating more rewards. Second strategy that people are known to apply is called directed exploration. So this strategy actively tries to reduce uncertainty you have about the decision-making problem. And in this case, this essentially boils down to selecting the option that you have observed fewer times so far. And in Horizon task, these two different strategies can be detected using two different conditions. There's an equal information condition, which is used to detect random exploration. So in this condition, participants first observe 4 choice trials where they are instructed to select a particular option and then get reward feedback based on that. And following these 4 forced choice options, they observe either 1 or 6 free choice trials where they can basically select whatever option they like. And then a choice is classified as random exploration if in the first choice trial, in the task with the longer horizon, it corresponds to the action with the lower expected value. because in that case, you control for the amount of information that you have, and then if you select the option that you think is worse, that means that you applied random exploration. The unequal information condition is used to detect direct exploration. So here in the unequal information condition, you again have 4 forced choice trials, but this time you have more information about one option than about the other option. So for example, 3 pieces of information about the red option and 1 piece of information about the green option. And here choice is classified as directed exploration if in the first free choice trial, you select the option that has been observed fewer times so far. So in this case, if you would select the red option, that would indicate directed exploration, because that means you would actively try to reduce your uncertainty about the reward distributions associated with the 2 possibilities. So people see, when people do the task, they see an interface that looks very similar to this, but this is not something that we can use to test a large language model on. And therefore, we have constructed a text-based version of the task that we can use to probe these large language models. Looks roughly as follows. We first give a general introduction. You're going to a casino that owns 2 slot machines, and you can earn money each time you play on these machines. And so on. Then we provide a list of previous observations, essentially saying you played machine F in the past and you got $51. You played machine J in the past, you got $39, and so on. Then we instruct the model that your goal is to maximize the sum of received dollars within a certain amount of additional rounds of playing, and we ask it which machine it wants to choose. And then the language model can choose a machine by simply completing this prompt, inserting machine F or machine J here. So we analyzed the behavior of these models again, and the first thing we did was looking at performance. In this plot here, you see performance of GPT-3 shown in blue and performance of people shown in orange. The x-axis shows the free choice trial, so how much information you have gotten about this particular problem that you're interacting with. And the y-axis shows performance again, measured in terms of regret. Lower regret again means better performance. And what we can see is that on average, GPT-3 is actually better than humans on this task, indicated by the lower regret. But when we look more closely at the behavior, we see also substantial differences between how large language models solve these tasks and how people solve these tasks. In particular, we see that GPT-3 basically does not get better at a task the more it interacts with it. It doesn't really learn, shows no learning effects. Whereas people, they actually get better if they get more information, and in the end, in the last free choice trial, they are in fact better than GPT-3 in this task. We also analyzed exploration behavior of both humans and GPT-3 in this task, and we found that GPT-3 sometimes engages in random exploration, meaning that it adds this noise to its decision-making process, and sometimes selects the option that it thinks is worse in order to explore the environment. In contrast to that, GPT-3 does not show any type of directed exploration behavior. So it never tries to actively reduce the uncertainty about the environment. And this is different compared to people, which are known to apply both of these strategies. So I won't go into much details here. Again, if you want to read more about this, feel free to check out the paper.
Out of curiosity, did you observe different results depending on whether you call the machines F and J, or for instance A and B or 1?
We did one ablation in the revision where we used 1 and 2 instead of F and J, and there we found that in this case the models were slightly better, but in terms of the characteristic behavior there was no difference. So you still find no learning effects, you still have random exploration but no directed exploration, but it certainly influences the performance. You had a question as well, Toby?
Yeah. So, I was wondering, can you really call it random exploration, or how can you be sure that
there's just noise?
Not just wrong,
yeah, good question. I don't have a good answer to this. It could be that it's just noise, but it's noise that is beneficial to solve the problem. Yeah. So one thing that you can do is you have these different control conditions, right? You compare essentially, is there more random exploration when you have a long horizon compared to random exploration in a short horizon? And that you find. So the model does more exploration in the long horizon cases than in the short horizon cases. So you have kind of this control here. Yeah.
Can you use exploration behavior with feature counting in any way, or does
you can definitely change the behavior of these models if you give them multiple tasks in a row. We have a preprint on this called meta in context learning in large language models, where we test what that changes. And there we show also it depends on the statistics of the distribution of tasks that you encounter. So for example, if you counter certain tasks that have more variance, that changes your exploration behavior in different ways than when you have tasks with less variance in the reward distributions. More questions? Yeah.
So usually in cognitive science, you will model this with reinforcement learning.
Exactly, yeah. And that is what we also, in fact, partially did. I didn't show the results here, but we essentially modeled the behavior of large language models using classical reinforcement learning models, and then checked, okay, how do they behave?
Okay, so what's the claim? Like, so the human is more like a reinforcement learning, more like a...
So yeah, good question. So essentially there are two different scenes here, right? One is it might be just interesting to compare the behavior of a large language model to human behavior, see what are the differences. So I think that is interesting to know. Another thing is also just completely taking the human out of the picture and saying we can use tools from psychology to understand how these really complex models work that we cannot really understand just by looking at their activations and weights and so on, and thereby learn something about how do they make decisions in certain cases and so on.
Okay. For me, for the human, it was, before I was like playing with this reinforcement learning model, and you have to outcode this action space, state space, and this kind of thing. Whereas here, you just show some tokens, and you have reinforcement learning for free.
Yes, in some sense, yes. What I'm not claiming in this part here is that these large language models or their behavior is a good model of human behavior. I think in the paper we kind of show, yes, there are some similarities, but there are also important differences.
Would you agree that compared to a reinforcement learning, like different kind of reinforcement learning, this is like more general? Because like you would have like one model that can do all the time.
Yes, and that depends what you exactly mean with more general, but definitely these large language models are more general than a Röskler-Wagner model, let's say, right? A Röskler-Wagner model you can only apply if you have some action space, some reward feedback, and so on. But here, these models, you can throw any language task in and you get an answer. Whether that is correct or meaningful in any way, but certainly they can solve a wider range of tasks than classical cognitive models. Cool, then let me quickly summarize the results of the paper. So in the paper, we looked at a bunch of different domains, including the decision-making and exploration domains that I presented a bit about, but we also looked at deliberation, where we investigated a two-step task, which some of you are maybe familiar with, and we looked at causal reasoning. And overall, we found that GPT-3, to our surprise, back then, at least 1.5 years ago, was reasonably good at performing in many of these tasks. One important exception was the causal reasoning task here. But then when we compared their behavior to human behavior, we found that there are also important differences. In some of these domains, you could reasonably argue that they have human-like characteristics, at least if you're generous. But then in other domains, behavior was completely different from human behavior. So to wrap up this part of the talk, I presented this idea that we can take experiments and paradigms from cognitive psychology and use them to study the behavior of large language models in order to better understand how they work. And I think this will become an increasingly useful tool in the future as these agents become more and more complex. And I think the cognitive psychology approach to study these models and try to understand them has several important advantages compared to the standard benchmarking paradigms that are present in the machine learning literature. First of all, these experimental paradigms from cognitive psychology have been often validated across decades of research. So they have been really established. as solid experiments. Then, in many of these experiments, tasks are procedurally generated. So there's not a fixed problem that you have to solve, but you can randomly generate new and new problems. And this is important because it allows us to avoid problems that come with data contamination. So in machine learning, you often have the case that some of these benchmarks that you want to evaluate the models on were actually included or might have been included in the training data set of these models. And then the question is, if you then test these models on these benchmarks, how meaningful are these results? And here you can avoid that by having these procedurally generated, randomly generated problems. And then finally, these experiments that were designed by cognitive psychologists do not only care about performance, but they provide also insights into how people solve the task. So you don't get only one scalar that tells you, can the model solve this task or not, but you often get many different values, or you get multidimensional measurements that explain behavior of these models. And I think that's interesting as well. Questions about that part of the talk?
Do you have any issues on why that region?
Why, in what case?
Like what causes the differences?
What causes the difference? So in the paper, what we have argued, and I think that is maybe a reasonable take, I think Andrew has some thoughts on this as well, but what we said is these models, large language models, are only trained to passively predict data. And cases where we found the strongest mismatches to human behavior were cases that have been argued in the past to rely on actively interacting with the world. So for example, causal reasoning. To do that, you might have to actively engage with the world, do experiments on your own, and that is maybe not part of the training data. And same with directed exploration. If you want to explore in a way to reduce your uncertainty within the world, that you could reasonably argue that requires you to interact with the world. But how these models are trained, that does not really happen because they're simply trained to predict the next word in a text sequence. Yeah.
So if you would have an agent interacting with the world, you would claim that by doing like next time prediction and next event prediction or something like that, you might get this other thing?
Maybe. Hard to say. I mean, without running experiments and doing entire studies.
I found it interesting that you have these experiments originally by scientists. Humans work on primates, and you just put it in a GPT model. Have you ever thought about having specific experiments decided to make and come up with what GPT model does, or you just want to rely on experiments used design back in the day with psychologists for humans?
I'm not sure if I fully understood it. Can you maybe rephrase it a bit?
You think you're lacking something by testing it on experiments that were designed to evaluate the behavior of humans? That you could get more insights by designing specialist studies?
Good. Okay, very good question. I think definitely you can, and it's also a big question whether the experiments that people have run on humans are actually valid to probe the constructs that are present in these models, whether there's actually a match between different kind of cognitive constructs that we find in people and large language models. And I think that is a big open question. But I would assume probably you can design good experiments that are specifically targeting abilities of large language models. Yeah?
Have you tried using different languages for the prompts?
No, we haven't.
Would it behave differently?
It's an interesting question. So what we tried in some of these experiments, we changed the cover story. So we moved from cover story that was about casinos to a cover story that was about financial investments. And there we found differences in behavior. So for example, in the financial investment case, these models were more risk averse. They made less risky choices than in the casino cover story. And I think that makes intuitive sense if you think about how people act in a casino and how they act when actual financial security is at stake. Yep.
Did the answers or the quality of the answers differ when you use the OpenAI ChatGPT website or the API?
So here we have only done this with the API, and that is because we needed to procedurally, or we couldn't manually characterize all the choices, right? For example, if you think about this choices 13K data set, there are like over 13,000 problems in this data set, and you cannot just enter them manually in ChatGPT, record the answer, and then go to the next problem, right? You need some way to do this automatically, and that really only works if you do it over the API, because then you can directly work in code. So we haven't looked at that. Yeah.
So you said that we can use this approach to kind of also better understand how the models work, and I for sure agree that this is the approach, but like in a sense we only get an IO method, right? Like it's really difficult to get any kind of internal mechanism explanations.
Definitely, yeah.
Generated explanations, there is a question on how reliable those are.
Yeah. I mean, it's the same thing that people discuss in psychology and neuroscience, right? If you run psychological experiments, you also get only an input-output method in most of the case, but then maybe there's something to add by running neuroscience studies, investigating internal activations, and so on, and I think that is complementary, definitely.
Would you say that like humans are as unreliable as models of explaining why we did certain things?
Probably yes. I mean, at a very high level without looking into details. Yep.
Just kind of going off that question then, one of the best kind of experiments are maybe done on like a large population of humans and psychologists for specific like mental illnesses, or like we're kind of designing experiments for the edge case of people. Are you also doing the same for models like these, and when they have hallucinations and you have serial effects? Like, have you tested this kind of problem solving across these domains for those edge cases as well?
Good question. So we haven't done that yet, but I think it would be super interesting to do that, because here essentially with people you sometimes have the problem, it's very expensive to run a big large-scale study where you test all of these cases, right? Where you have a diverse population, where you look at all the conditions and so on. But in a large language model, you can just query it. You get instant responses. It's fairly cheap compared to running human studies and so on. So I think that's definitely an interesting thing to do. Yeah. Maybe last question, and then we move on to the second part.
Yeah, I think it's quite to prompt engineer and more user-like behavior to bring a prompt behave like a human.
So we haven't done this in this project yet, but that is actually a good transition, because that is one of the things that we will look at in the workshop. So you will do it for me. Cool. And I think that is a really nice transition to the second part. So just a short summary of all the things that we have planned for the workshop part right now. So the idea of the workshop part is to familiarize yourself with large language models, in particular with some of the OpenAI models, get to learn how to query the API, how to process some of these results, and so on. The idea is hopefully by the end of it, you will have a better understanding of how large language models work and have some kind of feeling how to deal with them. And in this workshop in particular, we will look at different prompting techniques and see how these prompting techniques will influence the behavior of these models. And one of the things that we'll look at is also, can we find prompting techniques that make behavior more human-like? So for this, we need an experiment that we can look at. And at some time, a few months ago, I stumbled on this paper called Practice in the Case of Addition from Thorndike. It's quite an old paper from 1910. But I thought it's also only 3 pages long, fairly simplistic. But I thought it's like it introduces a very nice and simple problem that we can use to evaluate a large language model on. And essentially, in this paper, Thorndike administers a series of addition problems to people. In each of these addition problems, people have to add up 10 one-digit numbers. And they do that for 7 days in a row. And on each day, they solve, I think, 48 of these problems. And what we found back then is that even in just these 7 days of practice, people get better at the task the more they interact with it. Some of the results are extracted from the tables he provided in the paper. So note, this is like from 1910, so 100 years ago. Statistics were not a thing yet. There are no error bars, no nothing. But what you see here is the plot, so the day where people did the task. And then here on the blue y-axis, you see the number of mistakes that they make. And on the red y-axis, you see the time it took them to solve a particular problem. And what you see, at least on average, the decision time, the time they need to solve one of these addition problems, goes down as they get more practice. And also, quite noisy, but I think the general trend is there. Performance gets better over time. They make slightly less mistakes. And this is the kind of task that we will administer to one of the GPT-3.5 models, in this case, GPT 3.5 Turbo. In the GitHub that Toby has already sent a link around, but also I have the link on the slides later, there is some code provided for zero-shot prompting these models. And a zero-shot prompt in this case looks pretty much something like this. So you have these 10 one-digit numbers, have to add them all up, and then you have this equal sign, and then the model simply has to complete this equation by hopefully providing the correct result. If you do this in a zero-shot way, where you present each of these prompts independently, you get an accuracy of 75% around, so meaning that these models are reasonably good at these problems, but they are quite a bit away from being perfect. And then in the workshop, we will look at two different things. First thing that we will look at is whether GPT 3.5 shows practice effects, similar to the practice effects that you find in people. And then we also look at different prompting techniques and try to figure out how these prompting techniques affect performance. And basically, there's very little structure to it. You can work on both of these things. On only one of them, you can do pretty much whatever you like. And then in the end, we will gather again and collect some of the results. Before we get started, I want to present some ideas that that could get you started, but you by no means have to stick to the stuff that I'm talking about. So one of the obvious things that you can try is few-shot prompting. In few-shot prompting, you provide some examples of the tasks together with a correct solution. So here is a figure that I took from one of the original papers that introduced the idea, where the task was translating something from English to French. You had a bunch of English words, sea otter, peppermint, and so on. And then you provided the correct French translation, which I'm not trying to pronounce. And then in the end, you queried the model with the question, what is the French translation of the English word sheet? May I ask, why does that work? Why does that improve performance? And I think my intuitive understanding here is that if you are in a context where you have seen some of the problems together with their correct solution, that also makes it more likely that future solutions are correct as well. Simply, if you think about how these models are trained, they're just trained to predict the next word. And if you're in a context where the next word is the correct answer, likely the follow-up problems will also be answered correctly. Another thing that you can try is this idea of chain of thought reasoning. Different ways of doing it, but one very simple one is just adding that thing step by step to the problem or to your prompt. From the paper that I have here is an example that you have a juggler that can juggle 16 balls. Half of the balls are golf balls and half of the golf balls are blue. How many blue golf balls are there? And then you add additionally, let's think step by step to it. And then the model provides you with a reasoning of how it arrived at a certain answer. You can also apply that to this problem of adding up these 10 single-digit numbers. And why does that work? My intuition, at least, is, and probably there are many ways why this works, but mine is that it breaks down the problems into smaller sub-problems, and these are typically easier to solve. Another idea is this concept of self-reflection. So here the idea is you let the large language model generate an answer, and then you let it criticize its own answer, and then you can let it give an updated answer. I think this I got from a web page where the task was pick 5 random digits and multiply them together, and the model generates these digits, gives an answer, and then after that you would prompt it with something like, is that answer correct? If so, why? If so, why not? model would give some reasoning, and then you can ask it the same question again and see did that improve performance or not. On the source where I got this from, they stated that this might work because it acts as a denoising operator for LLM outputs. I have no idea what this actually means. My intuition is more like that it works in a similar way to why chain of thought prompting works, because it breaks down the problems into smaller sub-problems when you do this, explain why it works. Then we have this idea of role prompting. So here the concept is fairly simple. You instruct a large language model to take a specific role. One of the common ones is saying something like, you're a brilliant mathematician that can solve any problem in the world. And then you give it a math problem and you hope that the answer is more likely to be correct if you compare to when you would have excluded the prompt. Why does that work? Well, if you have a context where you mention the answer was produced by an expert, then it makes it more likely that the answer is also correct, just if you think about how these models are trained again. Yeah? Sorry, go again. I didn't get the start.
I'm curious, like, why this works that way. Have an expert that aggregates all the data on mathematicians in the first sentence and then loads it into the second.
Yeah, so intuitively, you can think about this model is trained on a lot of text, right? There's some, I don't know, text from forums such as Reddit, but there's also text from maybe mathematical books. And then I guess the answers in math books are more likely to math problems are more likely to correct than the answers that you find on Reddit or some of these forums, right? And then when you instructed, oh, you're a mathematician, that makes it more likely that it is in a context such as in a math book. Yeah.
I'm curious why that works at all, because it's like a multi-step task and can't like have not showing like immediate answers. Like how can you do that all at once?
How can it solve these problems in general, like these kind of problems? How can it do it all at once? Yeah. It's a good question, right? Because if I would give you that, you can't solve it either. You have to do this chain of thought reasoning. Yeah, good question. Yeah, but I think considering that, these 75% are actually quite impressive. Cool. And then the last thing, this is from some of the research that we did in our lab, is this idea of emotion induction. So here, concept is that we pre-planned our prompt with a text that induces certain emotions. So we did this in a preprint recently where we instructed a model to generate a text of around 100 words that makes you anxious or happy. And then we let the model produce this text. And after producing the text, we would ask, we will probe it on the problem that we actually care about. So here you would ask the 10-digit addition problem following that. And what we have shown in the paper is that presenting this emotion-inducing text also changes the behavior of these models. And if you think about it, maybe that is intuitive because, for example, if you're in a case where, in a context where it is more likely that you are anxious, that also means that you are more uncertain about how to solve certain problems, and that makes you, for example, in this case, less performing. And then you could look at, can you find emotions that make the model better at this task? Can you find emotions that make it worse at the task, and which ones? Cool. So these were just some examples that you can look at. My idea with the workshop part is kind of like it's very much freestyle. You can go as crazy as you want, figure out, get a feeling, if I change the prompt in that way or that way, how does that change the behavior of these models? There's some code provided on the associated GitHub. Here's the link again, but Toby said he also sent it around. In this GitHub, essentially, you only need, or you mainly need 2 of the files. You need this query zeroshot.py file, which just provides you with the code of zero-shot prompting the OpenAI models on these addition problems. And then you maybe also need analyze.py file, which just presents you with a very simple code snippet that allows you to evaluate the accuracy of these models. The problems are also provided in this problems.csv file. So this is in the data folder. in the CSV, you basically have the index for the run and the example that you are seeing. Corresponds roughly to run is the day that people do the experiment. An example is how many problems have they encountered on that day. And you have the 10 one-digit numbers, and you have the corresponding result. Let me briefly talk about this query zero-shot file, a fairly simple file. Let's first talk about the main part of the code. First, we load in the problems, then we loop over all the runs and over all the examples. We load a specific problem in. So this is just loading in this row, one row of the data file. Then we transform that row using a maybe somewhat complicated expression, but doesn't matter so much. We transform that row into the prompt that we want to use to query this language model. So this corresponds then roughly to, or exactly to this format. And then we simply query the OpenAI API with that prompt. Query is fairly simplistic as well. We set up an engine that we want. We provide the text as the content. We set the maximum number of tokens. For some of these different ways of prompting, you might want to change the number of maximum tokens. So for example, if you do chain of thought prompting, it could be that you need to generate more than 100 tokens. We use a temperature of 0 in this case, which lets you generate deterministic answers. Maybe you want to change that for some of the stuff as well. You can play around with that. And then there are some stop tokens here, which essentially tell you whenever you encounter a line break or space, the API will stop generating future tokens. And that is useful for the zero-shot prompting case, but for some of the other things, you might want to remove that as well. And then we have this kind of try and accept structure here. This is just there. Sometimes you get an error when prompting the API because it's overloaded. And by adding that, that ensures that your code doesn't die, but will just wait a bit and try again. And basically the idea is you should change the prompt in some ways, for example, in the ways that I have presented before, and see how that affects behavior. Maybe questions that you can look at is, how do you have to change the prompt to get better performance? But you can also look into ways of how you can make these models to get practice effects similar to the practice effects that have been observed in people. Questions to the code real quick. Perfect. Also, I will be around, so if during the coding part you have any questions, feel free to ask me. And then, what else do we need? So Toby sent the keys around.
So, in case you guys don't have access to the OpenAI API yourself, I will send a message in the Telegram group with keys that you can use. Please be mindful of the resources because we pay for it and that's shared for everyone. I will share several keys and I would ask you to grab the key according to the row you're sitting in. Like first rows go for key 1, key 2, key 3, key 4, key 5, last 2 rows, please. I'll send it in the Telegram chat.
That is perfect. And then I think I would ask you also to stick to the GPT 3.5 turbo model and not use models just as GPT-4 or so, because if everybody does that, we quickly run out of the allocated budget that we have for this workshop. Cool. And then how late is it? We have until 11, you said? So let's meet again at 10:55, and then we can discuss some of the results that we have and collect what kind of worked and what didn't work. Yeah, 10:50 to 10:55. And if you don't have a laptop, try to find a friend that has a laptop.